Alright, last video for chapter 6, 6.8, exponential growth and decay models. We're no longer doing Newton's law just for time and for the sake of everybody, me and you. We took this out. So don't worry about it. It's already out of your homework. If you already did it, I'm sorry. I thought I took it out of the homework last weekend, but my math lab has been having issues, so it could have just not registered that I actually did it. Um, so just sorry if you already did it. Now you know it, but sorry. All right, let me preface by saying there are not a lot of questions for this homework assignment, and there are not a lot of questions on the test for 6.8. So let me just preface with that, and we'll do the best we can for 6.8. All right, law of uninhibited growth or decay. So many natural phenomena follow the law that an amount A varies with time t according to the function a of t equals a sub 0 times e to the power of kt. Here, a is the original amount when time is 0. Cannot be 0, and it's a constant. K is always going to be greater than 0 because you're growing. The equation 1 states that the amount A is increasing over time. If K is less than 0, the amount A is decreased over time. In either case, when an amount A varies over the time according to equation 1, it is said the following exponential law, or the law of uninhibited growth when K is greater than 0, or decay when K is less than 0. Meaning, this is number 1. My bad. This is number 1. This would be number 2. I forgot to label them. And all this is saying is that if it's exponential decay, it goes down and your constant is negative. It's exponential growth if it goes up and your k is positive. Other than that, the equations are exactly the same. Alright. Since I recorded my earlier videos, like a couple years ago, I wish I had more time to actually re-record them and put in examples of what's going on right now, but I couldn't. But I just think it's kind of ironic that we're learning about exponential growth. I don't know. It's just funny to me. As funny as it can be. Alright, a model that gives the number n of cells in a culture after a time t has passed and early stage of growth is n of t equals n sub 0 times e to the power of kt when k is greater than 0. N sub 0 is your initial number of cells, so any n sub 0 is how much did you start off with. If right now, before any time goes, I have 1 bacteria, and let's say an hour later it doubles, I'll have 2 bacteria. Okay, K is going to be your positive constant, and that represents the growth factor of the cell. I'm sure you remember something like this in biology or math before, but it's just the perfect example because bacteria grows exponentially. And bacteria, viruses, all that stuff grows exponentially. That's why it's the perfect example. So a colony of bacteria that grows according to the law of uninhibited growth is modeled by the following, or by the function n of t equals 100 times e to the power of 0.054 t, where n is measured in grams and t is measured in days. So remember, t in math is always time. It will never, ever, 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 ever represent anything different. If it does, that mathematician just shouldn't be a mathematician. T is time, okay? So let's determine the initial amount of bacteria. So the initial amount, that's here. That's the n0. So since we know we're growing, because this is bacteria grows, we have our formula, n of t. We could just put n. T just means time. So our initial amount, which is n sub 0, times e to the power of k. The constant, we're actually giving it. But that's just our formula we're coming from. So if we plug in what we're given, this is what we're given. If we kind of like look at it and apply it to what we have 100 e to the power of 0.054 t. So if it's asking for the initial amount, what's in place of the initial amount? It's 100. So our initial amount equals 100 grams. So that means before we started anything, we had 100 grams of bacteria. I do apologize for my dogs barking or huffing or whining or that. I can't lock them up right now, but I usually put them in my office with my partner while she's doing work, but I can't right now, so you're just going to have to deal with them. Alright. So that's our initial amount. What is the growth rate of the bacteria? So growth rate is always your K. That's your constant. So what's in place of the K? It's 0.045. But we want a percentage. 0.045, that doesn't really mean too much to us. So we would say K is 4.5%. If you can't remember, you move 2 decimal places. That's why. Or you could multiply 0.045 by 100. So that's our growth rate. Alright, part C. What is the population after 5 days? So we're asking about what is the population after some amount of time. So we're actually given t, which is 5. So all we have to do is just plug it in. We have 100 times e to the power of 0.045 t, which is time, and that's 5 days. And we plug this into our calculator. So I'll actually show you how to plug this into your calculator. I've said it before, but I'm going to say it again. You can download the calculator I'm showing you on my screen. You can find it on Canvas under announcements. And it's very obvious which announcement it is. And you can download it for free for 6 months, okay? Alright, so let's plug this in. We have 100 E. E is second divide. That's how you get the little e. To the power of 0.045 times time, which is 5. And we get 125.23. So on the test and on the homework, I tell you exactly where to round. Here I don't, because I tell you explicitly on the homework. But it is approximately 125.2 grams. So after 5 days, you have 125.2 grams of this bacteria. Alrighty, part D. So part D is how long, that's always time, how long, you're talking about how long is it taking you, will it take for the population to reach 140 grams? So now we're trying to find when are we going to get the amount of 140 grams. So let's plug it in. We have 140 equals 100 times e to the power of 0.045 t. That's what we're trying to solve for. So first things first, we want to get as much away as possible from the variable of t. So the first thing that we can do is divide this out to get one thing away from it. So when we divide 140 by 100, we're left with 1.4. This is the only time really you can ever use decimals, and it's okay. And since we cannot solve this, 1.4 and e can never be the same base, we're going to switch this to ln. So we have ln 1.4 equals 0.045 t. Let's solve for t by dividing. And we get t is approximately 7.5 days. So after 7.5 days, you'll have about 140 grams of bacteria. Now that should make sense. If we go back and kind of look at the previous example of part C, 5 days is 125. So 7.5 days, 140. Yeah, that seems about right. So your answer shouldn't be weird. It shouldn't be like 3 days or 14 days. So it should be, your answer should make sense, okay? Alright, part E. What is the doubling time for the population? So we originally started our initial value. Remember, our initial value is n sub 0 is 100. So if we want to double it, If we want to double it, that's multiplying it by 2. So we want to know, when is n 200? So same, just like the previous example we did, the part D, we have 200 equals 100 e to the power of 0.045 t. We're going to divide by 100. And when we do, we're left with 2 equals e to the power of 0.045 t. There's nothing in front of e, so let's go ahead and switch this to ln. We have ln2 equals 0.045 t. Divide by 0.045. And we get t is approximately 15.4 days. And that makes sense because if we're doubling it, we're doing it 2 times. So 15.4 days makes sense. All right, example 2. A colony of bacteria increases according to the law of uninhibited growth. So if n is the number of cells and t is the time in hours, express n as a function of t. All that's asking is, what formula would you use? Since we're talking about uninhibited growth, we're going to be using n of t equals n sub 0 times e to the power of kt. That's all that means. Alright, B. If the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. So we're just finding the function. There, find the function. Alright. We don't have k. If you have k in your formula, you need to find it if you're not given it. Alright, so let's go ahead and find it. And we can find it by the information they just gave us. So they just said the bacteria doubles in 3 hours. Oh, let me switch that color. That is all the information we need, because we're given t, and we're given that something doubles. So we're actually saying we're doubling the initial amount. So we're doubling initial amount. Remember, initial is n sub 0. So whatever it is, this side of the equation is 2 times the initial amount. So we have 2 times whatever we started with, because that's what we're trying to do. We're trying to find out, when do you double the initial amount? And that equals whatever the initial amount was times e to the power of k and t. So we know t was 3 hours because it stated that in 3 hours it doubles the initial amount. So let's solve for k. Because these are on opposing sides and there's no plus or minus, we're allowed to cancel them. So we're left with 2 equals e to the power of 3k. There's nothing in front of e, so we can switch this. We have ln 2 equals 3k. Divide by 3. So ln 2 over 3 equals k. That means k is approximately 0.23105. And that's all it was asking for. It was just asking for what is the constant. Okay. Alrighty. That was part B. Part C. How long? So how long? What's it looking for? It's looking for time. I'll put part C right here. So it's asking for time. How long will it take for the size of the colony to triple? So we want to look for how long for the original value to triple. So we can have 3 times the initial value. 3 times what we started off with. Isn't that very similar to what we just did about the doubling in 3 hours? But this time we have k. So we're just trying to find t. So you see the only difference is the k and the 3. So we're going to pick it up. Nope, let's just do it the long way. Alright, so we know that we are going to triple whatever we started off with, and that equals whatever we started off with times e to the power of k. We have k. K is 0.23105 times t. We're trying to find when. So we're going to cancel those out. We have 3 equals e to the power of 0.23105 t. Let's go ahead and switch this to ln. So we have ln 3 equals 0.23105 t. Divide. And we get t is approximately 4.755 hours. So the colony will triple in about a little over 4.5 hours. Alright, part D. How long? So how long? We're looking for time again. How long will it take for the population to double a second time? That is, increases 4 times. That is a trick question. We actually don't need to do much math at all. Alright, so the population, we know something about it already. We know that the population doubles in 3 hours. It told us that. So, if we want to double it again, it's going to double again in another 3 hours. Because that's the rate. It doubles every 3 hours. So we have 3 hours, which is the first double. If we want to double it again, we have another 3 hours, which is 6 hours. Alright, last example. Remember, I took out the Newton cooling just for time's sake and just for everyone's sake, you know. I'd rather be there for you. Alright. Uninhibited radioactive decay. So instead of k being positive now, it's going to be negative because we're decaying. That's the only difference, is that if we're decaying, k is negative. If we're growing, k is positive. But everything else is the exact same. So every step is going to be exactly the same. Alright. Traces of burned wood, along with ancient stone tools and an archaeological dig, were found to contain approximately 1.6% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? This is 100% factual. This is how archaeologists approximate how old something is when they find it. I think it's pretty cool. Alright, so since we're talking about decay, and we know, say, like I didn't say decay before, we know it's decay because half-life. Half-life means you're cutting it in half every time, so you're decaying, okay? So we have A equals A sub 0 times e to the power of kt. And instead of using n this time, we're using A because it's ancient duels, we're talking about age, that's why. So A sub 0, that doesn't change, it's still your initial value. Your k is still your constant, but it has to be negative. And then we're actually given something, and I kind of talked about it before, half-life. If anyone has played the new VR, you let me know. The Half-Life VR, you let me know. I want to know how it is. Alright, so Half-Life means half of your life, half the original amount. And remember, original amount means A sub 0. Alright, so we're not doing multiple steps here. It's just asking us to find the approximate when the tree was cut and burned. So we have to do all the steps. We have to find K, then we have to plug in stuff and do stuff. So we actually have to do all the steps that we've already been doing, but in one problem now. So we're stated that at the time we found this tree and how decay works for radioactive material in carbon-14, it's half-life. So it's half the original amount. And that equals our original amount times e to the power of k, and we do have our time. It's 5,730 years. Because that's the half-life of carbon. Alright, just like before, we can cancel those out. So we have 1/2 equals e to the power, e to the power of 5,730k. Since there's nothing in front of e, we can go ahead and switch this to ln. So we have ln 1/2 equals 5,730k. Divide so we have ln 1/2 divided by 5,730, and the calculator, it's going to give you this. It may or may not, it just depends on what calculator you have. That's what your calculator is going to give you. All that means, it's a scientific notation. Yeah, throwing that back. Right, I haven't talked about that in a while. So you move 4 decimal places. So 1, 2, 3, 4. That means we have 3 zeros now. Because we only moved it 1, 2, 3, 4. So that's why you have 3 zeros, because then we have 120968094. And that's our constant. Alright. We found our constant. Awesome. That means now we have the equation a of t equals a sub 0 e to the power of, I'm so sorry for this long k, negative 0.000120968094 times t. Yeah, I'm very sorry for that. Trust me, I regretted making it that type of k, but we're just going with it now. Alright, so we need to solve for our time, now that we have constant, but we need to know, we don't have enough information here, because we don't know what a sub 0 is, so we can't solve yet. But there is something else it gave us. 1.67. It says that the archaeological dig they found to contain approximately 1.67 of the original amount. So that means whatever it is, at whatever we found, we had 1.67%. %, that is 0.0167. So when we found it, whatever the initial amount was, but when we found it, it had this much left. So we have 0.0167 equals e to the power of negative 0.001209688094 t. The reason why we can get rid of a sub 0 is because we don't care about the initial amount now, because when we found this, it had 1.67% of that initial amount. Since we know the constant, we know how much has it changed over the years. Since there's nothing in front of E, we can switch this to ln. We have ln 0.0167 equals negative 0.00120968094t. We're going to divide. So we divide by our decimal. I'm just going to do that. I'm not going to rewrite it. And when we do, we get time is approximately, my bad, there's supposed to be 3 zeros. There's 3 zeros. 3 zeros, 3 zeros. There we go. So we have time is approximately 33,829.96643. We can round that up to 33,830 years old. That means that tree was burned down about 33,000 years ago and cut. Cool, right? Alright, that is it for chapter 6. Good luck with it. Take your time. Make sure you're taking diligent notes. And remember, 6.8 is not heavily tested on, okay? It's just how can we apply what we've been learning about logarithms to the real world? And it's used a lot. A lot of scientists, biologists, if you want to be a chemical engineer, or if you want to be a doctor, stuff like that, you're going to use this chapter a lot, okay?